Welcome back. Everybody's all chatty, excited to be here, right? Always, yes. It's such a lovely day to come to school, wasn't it? Yeah. Yeah, that was sarcasm. It actually kind of reminds me of home. This is what Nebraska is like every single day.
Oh, wow.
I'm right, or she's right.
Oh, no, she's right. Whatever.
My other Nebraska representative, you knew what Arunza was, so you must have spent time in
I
Nebraska.
had a friend that got married in Omaha.
Okay, that's where my parents are. So, yep. So, yeah, this is Nebraska weather, which is fitting, actually, because my first announcement is that we are not having class on Thursday because I have to go back to Nebraska for a funeral. So, my uncle died. It's sad, but not terribly unexpected, but it will be very sad for my mom and my aunt, so we're going to go and try to do the family thing. So I'd like to welcome our special guest. Nico is also here to join us. He's like, why are you all looking at me? So that is to say that all of us are busy professionals, but honestly, we are all people first. So I'm taking time out of my day to be with my family. Her family is here because he needed to be here today, and if any of you ever need to bring someone to class, I don't care what the university policy is, bring them. And if you have to miss class for your families, miss class. That's why we stream. So just, that's good to keep that in mind, right? So I will, since we're not having class on Thursday, I will put up your next formative assessment before I leave town, let you know when that is available as well. And you have a homework that you're working on now that is due Wednesday. So I thought I would open up the floor for questions on that.
Yes, but I'm not where I need to be yet.
Okay, so you work on that. So let me give you some common troubleshooting tips that I've answered the same question about 5 times, and so I figured it might be good just to talk about it. So my strategy here in asking you for various things. So enter the residual variance is always first for a model, because if you have that right, you have the model right in terms of what the outcome is, what predictors belong in the model. The next question, the fixed intercept estimate. If you have that right, then the predictors in your model have been centered correctly also. So recall centering, the idea of subtracting or adding a constant to change the scale. There is no wrong way to center. You can pick any constant you want or none at all. The model still works the same. It still accounts for the same amount of variance. The predictor still has the same level of significance. It just changes where the intercept is. So that's why you will not get the intercept right unless you've centered your predictors correctly. So in the instructions, the first model says no predictors, empty model, which means that the fixed intercept is unconditional, so you can't get that one wrong. The second model is predicting fits thrown from pleases heard centered at 7. So this is going to require you to make a new variable. So the formula for that is always new variable equals old variable and then whatever transformation. So it would be like pleases 7 equals please count minus 7, for instance. And that new variable is what goes in the model. Yes, ma'am.
So how do you know that you're subtracting 7 and not adding 7?
Good question.
It
would be centered at
really dumb. Okay.
no, it would be centered at minus 7, and then you'd have to add 7 instead. So the idea is to shift it over so that 0 equals 7. And so in this case, what you would do is given the scale is all positive, that requires subtraction.
Okay, that makes more logic. Okay.
If you had a scale that was negative, then you might have to add to get 0 up to 7.
Okay, I see.
That happens pretty rarely, but it's possible. So yes, good question. All right, did you find your question yet?
Standardized estimate for the fixed intercept.
Yeah,
I'm having trouble finding.
It's not given because by definition, it's 0. Always. So there's a few that if you just randomly went through and started entering numbers, you enter 0 on that one, you get it right. And it's actually not given on your output for that reason, because it's always 0 by definition. The role of the intercept is to adjust for the differences in the means of the predictors and the outcome. And if it's standardized, then all variables have a mean of 0, so there's no adjustment needed.
Okay.
So it's the standardized slope. You can get that either, are you using Stata or SAS? Stata, it's a comma beta in the reg command, and in SAS you can either get it with procgeom select or procreg as a separate procedure to give you that, the standardized estimates. Age group is another predictor that shows up. It's already centered so that 0 equals 3 years. So then I'm asking for the predicted outcome for 3-year-olds and 4-year-olds. That's requiring you to determine how the model gives you each of those things. One of them is given already, and the other is a linear combination. And there's an example using married in example 4 that you can start to use that to figure it out. So any questions on any of these? Yes?
So for the result section,
Mhm.
when you're referring to the standard error, some of the choices have sample mean, population mean. When you say population mean, are you referring to the actual population or multiples of a sample?
The theoretical population.
Okay.
Yes, I'm particularly fond of this one. Yes, I thought that was pretty awesomely terrible. So
What?
this drop down choice that shows up about 6 times.
Yes.
Yeah, because that's as hard as it is to learn how to work with these programs that are completely non-intuitive and written in another language, it's even harder to know what the numbers mean when they come back out. So that's what we're practicing here. So, right? Because that's where the rubber meets the road, so to speak. Knowing what to do with the extras. All right. Other questions? Yes.
This might be too close to like asking for an answer. So you can tell me no.
Fair enough.
So I just want to confirm because I tried to look back and see. So if the slope is significant, does that mean that the reduction in variance is significant?
When, if there's only one slope in the model, then that is the only way the variance could have come down.
Okay, cool.
Starting today, when there's more than one slope in the model, then you're not sure which one did it or if it was a combination. Yep. Others? Okay, let me know if you have any questions. As I said before, it's perfectly acceptable to paste in code and error messages and let me know, say, what's wrong with this, or why isn't this working, or I've tried this and my answer's not correct. Can you point me in the right direction? I'm happy to answer those quick questions and help you get unstuck as need be. So this is due Wednesday night then. And office hours are later today at 3:15 in case anybody wants to come and chat through their responses. Otherwise, we finally get to part 2 of lecture 5 and example 5. So the common thread here is the idea that some predictors require more than one fixed slope to be able to fully describe how they relate to an outcome. And so there's 2 special cases of this that I wanted to introduce you to. One is the idea of a categorical predictor. So this is, example 5 and lecture 5 is what we're looking at. Categorical predictor. Otherwise known as analysis of variance. So when you have a quantitative outcome being predicted by a categorical predictor, and you need as many slopes minus 1 as you have categories. So that's the part that we looked at before, and then the new part is the idea of modeling a quantitative predictor that has a nonlinear relationship to the outcome. So that can take one slope of a different form, or it can take more than one slope, depending on how you want to look at it. So do you want to do a little bit of review before we jump into new stuff? That be okay? Yes. Emphatic nod? Yes. I understand. So let's see here. So one slope, things that you get for a single slope. So in your current homework, you're working on practicing this skill with a single quantitative predictor and looking at a linear relationship, as well as with a single binary predictor and looking at a difference between 2 groups. So for any one slope, such as beta 1 in a single predictor model, you get an estimate. That is the best guess for what that relationship should be in the original metric of the variables. So it is the change in y per unit change in x is the definition of a slope. You get a standard error for the slope, which is a measure of its imprecision. It would be how far off on average the slope is from the population slope. If you take that estimate divided by the standard error, you get your t-value. T, in combination with denominator degrees of freedom, sample size minus the number of fixed effects in the model, which right now would be 2, gives you a p-value for whether or not that slope is expected of that size if the true slope were 0. And we use a critical value then to choose whether or not it's significant. In practice, we end up with an exact t-value and an exact p-value from the software program. And we can convey an effect size that goes with this unstandardized estimate using the standardized solution. So that's what the beta option in reg and stata gives you, or else STB, I think, in proc reg, in SAS, and it gives you the standardized solution, which comes from this result here. It's what the slope would be if x and y were both z-scored, essentially. And if you only have a single predictor in the model, that that standardized slope is the same thing as the Pearson correlation. Okay, so that's one thing at a time. So we looked at then what happens if you have more than one thing at a time. So for instance, if I have a nominal variable like this, it can be ordinal or nominal, but the point is that we're treating it as categorical. We're not trying to put a single line through it. So we looked at an example of self-reported respondent class, low, medium, below, middle, or upper with respect to predicting income. So because we have 3 different categories, we need 3 fixed effects total to be able to perfectly recreate those 3 means. So that's an intercept, 1 fixed slope, 2 fixed slope to get to the 3. We can decide how to set up the predictors to be able to differentiate these groups. Let me go back here. So in this case, what I have done is take my original categorical variable, 1, 2, 3, for instance, and created one new predictor that I've called L versus M. So that is coded 0 for the low group, coded 1 for the middle group, and coded 0 for the upper group. So that predictor then distinguishes low and upper from middle. So it's lumping low and upper together. That's why we need the second predictor, which is L versus U for low versus upper, that further distinguishes low from upper. So when you put them both in at the same time, you get a unique mean for each possible category. The intercept is the group that is coded 0 throughout all of the predictors. So I know, because I set up the model this way, that the low group is the intercept. So their expected outcome is given directly by beta 0. The expected outcome for the other groups comes from working out the model here. Beta 1 and beta 2 are the slopes for each of my new predictors. I fill in the value for the predictors, the 0, 1 for each group, and it works out that the middle group is a linear combination. So is the upper group. Of the 3 possible differences, 2 of them are given directly by the slopes, and the third is again a linear combination. So all I need is beta 0, beta 1, and beta 2, and I can get all 6 of these quantities. So then the question is, in addition to just each of these groups different from each other, does group matter? So I'm thinking of group as one variable, even though it takes 2 fixed effects, 2 fixed slopes to fully delineate its effects. So I may want to know, in general, does group matter, to try and put the fixed effects back together again to answer a question about them jointly. You may hear this language in other classes. I'm asking about an omnibus effect. That term means more than one thing put together with respect to a single predictor. So if group matters, if beta 1 and beta 2 jointly are different than 0, then that is the same thing as saying the residual variance that's left over in income after I predict it with class is significantly lower than the variance that I started with. In other words, the model predicted y hat that comes from this equation is significantly correlated with the actual y. So these 2 ideas are related to each other through squaring. So the first question, is the residual variance significantly lower than the total variance? That is going to be answered as r square. Variance is square, remember? The other one, the correlation is r. If I squared that correlation, we get r square. So these are 2 It's the same idea said differently and differing by a function of a square or not. If the y that's predicted by the model is significantly correlated with that y, we take that correlation and square it. That is the difference in variance between the two models. It works out to be the same idea. So how we ask for that then is what's called a multivariate wall test, and that's using our new friend f. So we have to know two things in terms of the number of fixed slopes, how many we estimated to be able to get that level of prediction, and how many are left over. Those are numerator degrees of freedom and denominator degrees of freedom, respectively. We end up with, let me go to this table here, a ratio of information that we gained over information that we could have gained but haven't yet. So explained over unexplained is the idea here. If we take SS model here, sums of squares, this is like the numerator of variance. The difference between the y that's predicted by the model and the average y, sum that up across people, and divide by k minus 1, so that's the number of fixed effects minus 1. The minus 1 is because we already have the intercept and we don't count that as part of our prediction. We end up with this thing here. If we do the same thing for the unexplained, the difference between what the model says y should be and what it actually is, divide that by the number of parameters left over, degrees of freedom denominator, then we end up with f as the ratio of this to that. So f is telling us whether or not we have captured a significant amount of information relative to the number of parameters it took to get that information. So it's averaged, essentially. So if one of our slopes was fantastic and the other was not as fantastic, f would capture a weighted average. See, I dodged a swear word right there. Not as fantastic. It's like I'm back in Brigham Young again. Did I tell you this class that story? Oh, that was the other class. Okay, yeah. Once I gave a 4-day workshop at Brigham Young University, it was so hard not to swear. Yeah, one day I said crap, and this one lady looked at me like I had slapped her still. And I was like, that's not a swear word, come on. Anyway, fantastic or not as fantastic, the f would average those two together. So you can think about f as a function of information explained over information left over, each corrected for the amount of parameters it took to get there, or you can think of it directly as a function of r squared. So why are we just now talking about that? Let me go back here. Because if you only have one predictor, Terry, your question answered, then the t-test for the effect of that one predictor, beta 1, t squared is f. So if that beta 1 is not 0, then the r squared created from it is not 0. It's a one-to-one correspondence. It's not the same if we have more than one beta slope in the model. Then f is judging all of them simultaneously. So the r squared then is basically the amount of information in total minus how much is left over divided by the total. So it's a proportion of information that your model has explained. All right, how are we doing? Okay, so in terms of testing stuff, this little table here will help you remember.
Thanks.
Okay. If you're testing one slope at a time, that's your univariate wall test. That's your t. Estimate divided by standard error gives you t, gives you p. If you're testing more than one slope jointly, that's f. And then you need to know how many slopes you're testing as well as how many denominator degrees of freedom are left over. If you only are testing one slope, t squared is the f. They're one and the same. The top ones are probably never going to show up again for you, but this is ignoring denominator degrees of freedom. They show up in some programs for multi-level models as well as for something called structural equation modeling, which is like 4 classes down the road. They'll come back then, but we don't need them for right now. So in your next homework, which I have not made yet, I'm going to ask you to do something like this example here, where we're doing grouping variables and testing differences between groups. Although I may give you 4 groups instead of 3, just to see if you can extrapolate, right? You can do it. I have faith. I do. So effect size then. In this type of model, we could get, let me find it here, an R, a standardized slope for each of our beta 1 and beta 2 that describe the mean differences between the groups. But that can be less intuitive than another type of effect size. So this is our friend D, and I think we talked about this last time, right? Cohen's D, he gets credit for this one, although there's a bunch of other variants. But the idea is that it's a standardized mean difference. It's how far apart your group means are in standard deviation units. And you can get that by looking at the means and the pooled variance across groups. You can also get it directly from the results of your model. So D is 2t divided by the square root of denominator degrees of freedom. And so then you can use that for study sample size planning purposes. So I had this here just to show you how this might play out in practice. So I gave you power tables once upon a time, a couple weeks ago. And there's ones for D, and there's ones for R. So R goes from -1 to 1. D goes to infinity. Or a negative D would be like a mean difference in the other direction, and positive D would be a mean difference in the positive direction. So they're not on the same scale. D is not bounded, which is why you can have Ds of 1.4. So all the way out here would be means that are 1.4 standard deviations apart. That's how you would interpret that. So that's a huge difference. So what would it take in terms of these results to say that I have a sufficient power? Well, the difference between low and middle class, my slope was 8.85. Let me make this big again. Standard error was 1. So my t ratio, if I forgive the rounding error, I'm using it from the output, is 8.82. My d is 2 times my t divided by the square root of my denominator degrees of freedom. That works out to be 0.65. I go to my table. I find 0.65 somewhere between here. What is my conventional level of power that people say is good enough? Yep. Is that arbitrary or set in stone? Arbitrarily set in stone, yes. That's just what people decided a long time ago. And we go. So I need, in order to have 80% power, so if I did the same study over and over and over again, 80% of the time, my D of 0.6 would be significant if I had at least 45 people. This current sample has 400 and some, so it's not surprising that it was significant. Next one, low versus upper. Now this one, 11 or so divided by 3, that works out to be a smaller effect size because there's more variability in this case. Upper doesn't, we're not as sure about what the standard deviation would be. So it results in a smaller effect size if you have a different standard deviation. People will get into fights as to whether or not you should use a group-specific standard deviation or pooled. I'm going to be agnostic on that, but just know that there's a controversy to some extent. But a D of 0.3-ish is a lot smaller. So if I go down to my table here, I need about 175 to have an 80% chance of saying that a D of 0.3 is significant. M versus U, that was a very small effect size. It was not significant. Very small effect, I should say. A D of 0.05, so not very far apart. Even if I round up to 0.1, I need like 1,500 people to say that a D of 0.1 is significant. That's a lot of people. And last but not least, the R square. So these two slopes that differentiate low and medium and low and upper, and by extension medium and upper, those two slopes created a model R square of 0.1. So 10% of all the variance in income was attributable related to predictable by respondent class. If I take the square root of that r squared, that's 0.3. 0.32 here is the correlation between y hat and y. I can look at power for that too. A correlation of 0.3. Let's go back to my R table here. I need about 85 people to find a correlation of 0.3 to be significant.
So does it matter? Oh, you unsquared it. I get it.
I unsquared it.
Okay.
Then it's back in R.
Okay.
So yeah, you have to know whether you're in R square or R to sort of know what these numbers mean. That's also a source of debate as to which one you should give people. I can't pretend to care about that.
Did you give us like what r squared means? Or that was somewhere, right?
R square, you can think about it two different ways. It's the square of the correlation between y hat and y. So the model predicted y and the real y correlated, square that correlation, that's r square. You can also think of it as the proportion reduction in the variance that's left over relative to what it was to begin with. You can think of it either way. Okay. So how many different effect sizes are on this slide? Count them up. 1, 3, 4, right? And each of them has a different sample size need. So which one's the right sample size? The most, that'd be the one to guarantee. But let this be a lesson when people say I need to do a power analysis. Power for what is always my first question. Because there's no such thing as power for the whole, everything at once. You'd have to see what has the most need and power up to that, and it might be overkill for other parameters. So there's a lot more specificity that goes into sample size planning than is readily apparent sometimes. So yes. So intermediate summary then, we can jump back in and get to some new stuff. So if I have one fixed slope, if that slope is significant, I know r squared is significant. If I have one fixed slope that's significant, I know that the variance I have now must be lower than the variance that I had before. That one fixed slope has created a y hat that is significantly correlated with original y. And so the t value that comes from my one fixed slope squared would be my f for the model. The standardized effect, that would be my r, would be my r squared for the model. There's a one-to-one correspondence. When there's not a one-to-one correspondence, when you have two or more fixed slopes to describe the effect of a single predictor, or it will be multiple predictors next, then we got to know both things. We would want to know if each fixed slope is significant, as well as when they work together, if they create a significant reduction in variance. A significant explanation of variance is another way of saying it. If so, then I can say that I have a significant correlation between my model predicted y and my actual y. The square of that correlation is my r square for the proportion reduction in variance. Okay. Questions or any of that you want to hear again? Okay. Some no cool stuff. So do you remember the problem with Pearson's correlation? In terms of kinds of relationships it was capable of indexing? Linear. What does linear mean?
Line.
Line, yes. Like straight line, right? Straight line. Not bendy line, not line that sort of shuts off, but straight line. So if you have a relationship that is not a straight line, Pearson's correlation can't index that. And I said, you need a model instead, right? You get your model today. And by the way, this is something that I spend a good month on in my longitudinal analysis class and talking about the effects of time. And I thought, why can't I talk about this way sooner for the effect of any x, not just time? So here you go. So this won't be in any of your textbook stuff. This is more of an advanced thing, but I think we can handle it, don't you? I think so. I can totally, we can do this. This is within your wheelhouse. I think that this is one of those topics that is underrated in its importance and utility. So I'm bringing it front and center to you guys. So here's 3 different situations in which we might be interested in some kind of nonlinear relationship. And it turns out that I was able to use the GSS data for this without even really messing with it, because these things just happened organically. I didn't even have to like force it. So first is to examine slopes that are curvilinear, bendy relationships, as it were. And so I'll teach you 3 different examples of this that are fairly commonly found, at least in the kinds of data that I look at. Another is something called piecewise slopes or linear splines, where the slope for a variable is different in different sections of the variable. And then last but not least, an example of how to test whether or not you can treat ordinal as interval. Remember that ordinal treated as interval? The idea that you might have a variable that's like a 7-point scale, like strongly disagree, disagree, and you want to fit a line through it, right? Even though those aren't really numbers. Well, it turns out you can test whether or not the slope between each of your things is equal, and whether or not it's reasonable to put a line through an ordinal variable. So we will see those. So first off, curvilinear. There are lots and lots and lots of different types of curved functions. I'm giving you 3. But literally there are probably dozens, if not hundreds more. One is quadratic. Is this a word that you've heard before? Like parabola, would that be U-shaped? So there's upside down U and then there's happy face U. And I don't remember the words for those other than that. So if what you've seen so far is just a linear effect, like if I put x in by itself, that's what we get, is a linear slope. If I take x and square it, then when I put the 2 together, what I end up with is that curvilinear relationship. And so we create a quadratic trend by putting them together. This type of trend is good for variables whose effects change directions. So I'll show you some pictures of that. But you can think about the classic example of stress and performance, right? Like a little bit of stress, like you don't really care, not so good. Too much stress, so you choke, not so good. Stress sort of medium, that's where you want to be. That's the upside down U sort of thing. So quadratic is useful for those sorts of relationships. Exponential is another type of curve that you can get if you take a natural log transformation of your predictor. And that's a type of relationship that sort of shuts off. Like something matters up to a point and then it really doesn't matter that much anymore. You can think of like a practice effects curve. Like a little bit of practice helps, but at some point, like more doesn't really help. You just kind of, you're where you're going to be kind of thing.
Plateau.
Yeah. Plateau or asymptote. Yeah. Logistic is a type of curve that results from understanding that x has boundaries. So if a slope wants to keep going forever and ever, a logistic curve makes it sort of asymptote to a bottom plateau as well as asymptote to an upper plateau. It's an S-shaped curve. So I'll show you some pictures of what these things look like and then we'll do some examples. So first, quadratic. So those of you who are math people, you're going to love this one because it has like derivatives and stuff. For the rest of you who are not math people who don't love derivatives, no worry, you can just memorize the rule and then you're good. So what happens is that a quadratic slope takes the linear slope and it does one of 4 things to it. There's only 4 kinds in the world. It takes a linear slope and it makes it more positive, it makes it more negative, less positive, or less negative. That's it. That's all it can do. And the rule is we take the quadratic slope coefficient that we get and multiply it by 2 to describe what it does to the linear slope. The reason we multiply it by 2 is because we're actually talking about the second derivative of the function with respect to the predictor. I have this here to remind you. If that doesn't jog any memory, no worries. I'll just teach you how this works. So this is an example from my longitudinal class, actually. This is from my textbook, chapter 6, looking at examples of different types of quadratic functions where the x-axis is a variable for time. So it doesn't really matter what x is, but note that it starts at 0 so that the intercept is meaningful with respect to the predictor. So in each of these pictures, I have a linear slope that is this little tangent line to the curve here, starting at 0. That is either positive 4 or negative 4. So let's take the upper left here. At 0, the slope of this line is 4. For every additional unit of x, time, this linear slope for time becomes more positive because I have a positive quadratic slope of 0.3 by twice the quadratic. So by 1 more unit along x, the slope is 4.6. Another unit, it's 5.2, 5.8, and so on. So this is an example of taking a slope that is already positive, and as x goes on, the slope of x gets even more positive, an acceleration. So an example of this would be something like bacteria growth on a sponge over time. It just sort of, multiplies. Of course, my husband and I disagree about how to solve that problem. I throw the sponge in the dishwasher, and he wants to throw it in the microwave. So I'm like, why can't we do both, right? Well, I'll wash it, and then you boil it, and it should be fine. Or we just get a new sponge out. Because at some point, you just give up and get the new sponge out, right? That's like, oh, this is black. Like that can't be good. But anyway, I digress. So more positive, less positive, more negative, less negative. Those are the only 4 kinds. Top right is less positive. So same slope of 4 at time equals 0, x equals 0, but now the quadratic slope that goes with it is negative 0.3. It takes that positive slope and slows it down, makes it less positive by 0.6 each unit. So it starts at 4, it goes down to 3.4, another unit it goes down to 2.8, and so on. So this would be something like learning a practice over time. You practice and you improve a lot, but eventually your rate of improvement starts to slow down.
Yeah.
No, question? No? Okay. So the top 2, more positive, less positive. Let's do bottom left. Yeah, bottom left. This is a less negative. The slope at 0 is negative 4 down here. It is paired with a positive quadratic slope, so it takes that negative slope of 0.4 and makes it less negative, slows it down, so it goes 4 and then minus 3.4, minus 2.8, minus 2.2, and so on. And accelerating negative then is a more negative. Both coefficients are negative, so the quadratic enhances the linear. So the linear slope at 0 is minus 4. It becomes more negative by twice the quadratic, minus 4.6, minus 5.2, and so on. So an example of this, unfortunately, terminal decline in aging is a phenomenon sort of where you have a cliff and you kind of fall off it, and you have accelerated loss of function, as it were. So these are examples of linear and quadratic trends working together to create something that's sort of mostly linear, but it has a curvature to it. So let's take this top right picture here. What does the model say is going to happen if we keep following this curve longer? Yeah, it comes back down, right? That's what it says. So quadratics are good for approximating nonlinearity within a certain range, but they're also sort of theoretically dissatisfying. Because if this were learning, right, so kids are growing, the model would predict that as they keep growing, they start doing worse and worse and worse and worse, and that's probably not likely. So quadratics really are designed to capture effects that change directions, not just effects that sort of level off like this. Level off would be a different kind of curve that I'll show you next.
Is there an example for the decelerating negative function?
This one.
Yeah, so like you told us, like
Oh,
bacteria on a sponge. It's just helping.
This one, I think you could also say it would be learning if the outcome were something like response time, where like the time it takes to do something gets shorter and shorter and shorter. And so initial practice, it goes down quickly, but then you sort of level off. All right. Other questions? All right, so here, the GSS data we've been playing with. What I did to make this picture is I have a bigger version of the data set now where I have people from ages 18 to 76. I took the mean across people at the same age and I made this picture. Where the black line is the mean at each age and the red lines around it is plus or minus 1 standard error of the mean. So we have a lot of noise in the picture, particularly out here, but you can fairly clearly see a quadratic sort of pattern. Right? Income increases up to some point, like yay, middle age, and then it starts to go back down again. So we could fit a line through this, but that wouldn't be a very good fit to the pattern. We need a bendy line, a curvilinear line. So I fit this in SAS and Stata, and we'll look through the example, but here's some coefficients so we can get the hang of what this would look like. So here's my model. Income equals beta 0, my fixed intercept, plus beta 1 times age sub I minus 18. So that right there tells me age is a predictor, is my x, it gets the I because it's a variable, right? I have subtracted a constant 18 from everyone's score. So right now, this tells me what beta 0 means. Beta 0 is my expected income for what kind of person? Age 18. So still Jeff, you asked me earlier if I had to pick the mean as my centering constant. Nope, I picked the beginning. Because why not, right? Because that's the range of data. The intercept is sort of my jumping off point. That seems reasonable to me. I could have picked age 75 too and started from the end if I wanted, but why not? So this is my you are here sign, right? Predicted income for an 18-year-old is $2.6 thousand. That sounds pretty familiar. I think that's what Walmart paid me to stuff shoelaces back in shoes when I was 18, give or take. Yeah, didn't you not hear that story? No, that was my freshman year of college. I stuffed shoelaces in open shoe boxes at Walmart for $5 an hour. Yep. And here I am now, winning. So from here then, I have age squared. So it's the centered version of the variable, then squared. So order of operations matters here. So when you're centering predictors in your homework, you want to make the centered version and then square it as a new variable. And actually in SAS, you don't have to make the new squared variable. You can just enter it directly. But I have beta 2. So now the idea of the model is I'm asking, does age predict income? But it takes two slopes to answer that question, linear and quadratic, because the effective age is nonlinear. So I'm hypothesizing a quadratic trend and asking the model to give me the best fit estimates to predict that trend. So linear age slope. So if I didn't have this quadratic here, what's a slope? This one you got to know off the top of your head.
Still.
Hmm?
Like a line or?
Yeah. What? Yeah. If I said the slope is 2, what's that mean?
The difference of y from the mean.
Close.
She stopped it.
So if I said the slope is 2, it's the difference in y is 2 per 1 unit x. Yeah. So if I said the slope of age is 2, then that would mean for every year older you are, you get $2,000 more, right? If the linear slope were all by itself, that were true. But in this model, this beta 1, because of the interaction term with itself here, the quadratic term, it's conditional. In physics terms, this is the slope of the line tangent to the curve at that point. It's the rate of its velocity at a certain point. So it's the rate of change at age 18 specifically. And why I make that point, let me go back to the picture here. The whole idea of a quadratic trend is that here's my slope, my linear slope. It changes. It's either going to speed up or slow down as time goes on. In this case, the slope at 18 looks positive. It's going to become less positive as time goes on, and as less positive gets to 0, it's eventually going to head into the negative category. I think I just said category. That's a different word altogether. So it's important to be specific about which linear slope you're talking about. If I had centered age in the middle, instead, the linear slope that I would get back for beta 1 would be this one. If I had centered age at 75, it would be that one. So just like the intercept is conditional on when x is 0, in this model, beta 1 for the linear effective age is conditional on when age is 0. Same idea. So at 18, for every year older you are, you're expected to get 1.2 thousand more dollars at 18. The quadratic slope is negative, as we would expect based on the picture. So that rate of increase slows down as age goes on, and it slows down by twice this quadratic coefficient per year. So this is a less positive trend. So the model gives us the predicted income at 18, and it gives us the linear age slope at 18. But through a linear combination of the model parameters, we can get what the predicted income is at any age, as well as the predicted change in income at any age. So to show you how that would happen, I've done some linear combinations here, and this is what we would use our friend estimate for in SAS or lincom in Stata. So first one. Predicted income at age 30. We start with beta 0. So beta 0 is my intercept. That's the 2.6 thousand for an 18-year-old. We add to it the effective age and age squared. So if I want the predicted income for a 30-year-old, why did I fill in 12 for age? Because we started at 18. People screw this up all the time. Even like really, really advanced people screw this up. So just keep in mind the centered variable is what you're plugging in here. We are 12 past the starting point of 18. So I plug in the linear coefficient times age, and then the quadratic coefficient times age squared. And I can do the same thing for a 50-year-old, for a 70-year-old, and these are the predictions. I can also find out what the linear slope is at any point. So at what point is it that you hit the maximum, so to speak? I could find that out. I start with what the linear slope is for an 18-year-old, that's beta 1, and I fill in the quadratic and twice the age value that I want the linear slope for. So those are my slopes. So at age 30, the slope is still significant. It looks like if I take this estimate divided by standard error, it's not significant at age 50, and it starts to become significantly negative by age 70. And a little bit of math, you can figure out where the maximum point is. It works out to be minus the linear slope divided by twice the quadratic, plus 18 to get us back to the original scale, and it works out to be 48. So only 6 more years and I hit the maximum. Yeah. Yay, middle age. So how'd we do? This is what it looks like. I say that's pretty damn good. Considering I didn't make up these data, like this looks made up good to me. But yeah, the black line is the fit of the model. So all programs will do this for you. You can create a data set of predicted values, and you can plot them against whatever you'd like, the real ones. So the red lines are the prediction standard errors, plus or minus around the mean, and then the original data you can see there. This is what SAS gives you out of GLM by default. That's the scatter plot, as well as the predicted curve. And if we wanted to know whether or not the model captures significant variance in income as a function of age, then that's our F-test. So this is my summary of what you're going to see in the table. So F, numerator degrees of freedom. Where did 2 come from? Two slopes, yes. So what I'm asking is the model significant? Did these two linear and quadratic effects of age working together significantly reduce income variance? Did they significantly explain variance in income? I have 2 slopes. 731 is my denominator degrees of freedom. That comes from my sample size of 734 minus the intercept and the 2 slopes, 3 fixed effects. So roughly speaking, I could put in 731 more slopes if I wanted to. So my ratio of information known over unknown is 47. That's really good.
Can you say, so the relationship, can you do that one more time?
Yeah. So F is a ratio of information known over unknown, corrected for the number of things you had to spend to get the known versus the unknown. And that ratio is 47, so that's really good. I don't know what the critical F is for this degrees of freedom, and I don't need to. The exact p-value is less than 0.001. So it would be really, really unlikely to get this level of known information if the true slopes were 0 in the population. Way out on the right side tail. MSE is what it's labeled on the output. You know it as a special term, aka the first thing I ask for in any model you're going to fit. Residual variance. Yes, variance left over is 169. So we are at 169 for our variance that's left. The R square for the model. This is the proportion reduction. So age, the linear and quadratic effects of age, we're able to explain 11.4% of the total variability in income. Said differently, if we take the square root of this number, the correlation between y hat from the linear and quadratic effects of age and the original y is 0.338.
So does it beget logic then that if I didn't know that that was already significant, that I could take the R, go to the R table, look at 0.4, and then see that since the sample size is bigger than what it suggests, that it's like super powerful? No.
Not exactly. The table would give you the proportion of replications in which you would get a significant R of that size given that sample size. So the table's like forecasting.
So you can't use it reactively, really only preactively.
No, you could find an R values critical table if you wanted to, but that's what this is telling you is the exact p-value that goes with this. So one other thing to mention, this quadratic age slope is significant on its own. That means that we need to keep it in the model. Because we have a quadratic age slope, we have to keep the linear age slope too. It's a lower order term. They work together. The quadratic is not the quadratic without the linear there with it. Because what the quadratic does is take that linear slope and make it more positive, less positive, more negative, and less negative. They work together in the equation. Okay. So that's one kind of curvilinear relationship, something where the type of relationship changes in a gradual way. Here's some other pictures. These pictures create are pictures of exponential curves. The poor man's version of exponential that comes from taking time as an x variable and taking the natural log of it. Remember what log is? We saw log like 2 months ago or something. It's an example of a nonlinear transformation, right? So it takes the upper end and sort of squishes it back in and takes the lower end and brings it out. So if you look at the slope of the black line here in the bottom left picture, that black line is a linear slope. If you plot natural transformed log x against your outcome, that's what you get. If you unlog x, exponentiate it, that's the x-axis on the top set of pictures. That same line looks like this instead. It looks bendy. It looks plateauy, asymptoty, like diminishing returns. Like, does money make you happy? Well, yeah. Like, you know, making $2,000 a year did not make me happy, but at some point, right, more doesn't help. That kind of curve. So truly nonlinear models are tricky to estimate, but you can approximate that type of relationship by taking your predictor and taking the natural log of it and entering that into the model as a linear effect instead. You can also take that logged predictor and estimate quadratic effects of it to create different shapes. So for instance, this blue line here is a positive log linear effect paired with a negative quadratic log linear effect, and that makes it diminish even faster. So these are things that are, like I said, a little bit advanced, but I just want you to keep in the back of your head that linear is not the only game in town, and that nonlinear transformations can help you create these sorts of shapes. Also, here's another one. Your friend, the logit. Logit, yes. Now, it is the natural log of this quantity here. How far away you are from the minimum over how far away you are from the maximum. It creates S-shaped curves that look like this when plotted against the original predictor. So these sorts of relationships are designed for either predictors or outcomes that are bounded, and they can't keep going. So you will see this in advanced courses on psychometrics. Item response theory uses this type of logistics on the outcome side, as well as next semester, if you come to generalized models, this will be how we predict binary outcomes. So we have a binary outcome, say that's 0 as the lowest and a 1 that's the highest. We need a curve that understands it can't keep going and shuts itself off on each side accordingly. Okay. So those are examples of curvilinear trends of different kinds. I want to show you something else. Piecewise slopes. So this is a real-world example that is a good example of this type of approach. So I once taught a longitudinal workshop. It was a destination workshop series that Jonathan and I ran for 2 years. We called it Stats on the Beach. I'm not kidding. We did this because most workshops are in places you don't want to go to, and we thought, well, what if we could pay for our vacation by teaching for a few days? And so yeah, we went to Hilton Head Island 2 years in a row. We met every day from like 8:30 to 11:30. We gave them a boxed lunch, told them to go enjoy the beach. We reconvened at like 2:30 to 5, and it was glorious. So one of the participants in Stats on the Beach was there with this story. He was tasked as, it's a real world example, there was a series of houses in a state that were determined to have a whole bunch of radiation problems. And some of the houses got fixed and some of the houses didn't. They were below the threshold for where it was officially a problem. And the people who got the fixed houses filed a lawsuit saying that this whole remediation and the publicity around it ruined their property values. And he was called on as a defendant to sort of see if there was any empirical evidence as to whether this actually happened. So he had data I've de-identified the data, but this is the curve though. So what happened is that we had two different types of houses. The remediated ones were the green, and the untreated ones are the red. And after 6 years into this collection of data, there was a public meeting about the need for potential remediation. So people became aware of the problem. There at year 14 was when cleanup actually started. And so they were interested in whether or not house value was diminished by sort of the stigma of needing to be remediated. And so you can look at house value not only as sort of how much your house costs relative to comparables, but also how it grows in value over time. And so this is an example of a piecewise analysis, as it's called, because there are distinct sections of this variable where we want to know if something changed with respect to the intercept or slope before versus after. So we have a hard line in the sand where something happened, and we want to know what happened before versus after. So I have some code in here to show you how you would go about coding these different sections of time. So the SAS coding, I think, is a little more intuitive. What would be required to have 3 different sections here is 3 new predictors. So one is the change in the outcome from years 1 to 6. Then we want to have another one pick up where that one left off and have the change in the outcome from 6 to 14. And then another one pick up where that left off and have the change from 14 to 18. This coding accomplishes that. So the intercept is the first occasion. So if year is greater than or equal to 1 and less than or equal to 6, then my first slope, S1 here, is the name of the variable I'm creating, is the year minus 1. And the other slopes are not yet active because they're for later in time. Once we get past year 6 and up to 14, the first slope leaves off where time left, so 6 was the end of the slope, and the second one picks up and tracks the change after 6. Likewise, between 14 and 18, the second slope leaves off at 14, and the third slope picks up. So we can test for the significance of each slope as well as the differences between them. Here's another example that you guys are already familiar with. In example 4, we looked at the effect of years of education on income. At the time, it was family income because I didn't realize there was a better version in the data set, so this is individual income. So I created the same sort of plot by averaging across all the cases that have the same year of education, creating a mean for each of those subsets, and then plotting the means. So in this data set, education goes all the way down to 2 years as the low, and it goes up to 20 years, again, as the high. And what this looks like to me is a 3-piece model as well, where if you don't graduate high school, basically 11 and anything under that, there's really no effective additional education. Like, it doesn't matter if you dropped out in 3rd grade or 11th grade. You don't have a high school degree. You don't get to check that box on your application. If you graduate high school, ta-da! And after that, more is better. But up to a point, right? This sort of looks bendy a little bit. So this would suggest the need for 3 different kinds of slopes to be able to describe the effect of education on outcome. So I am hypothesizing 3. So I'm setting it up so that the intercept is at 11 years of education in this case. So the middle point here. So I have one slope that I'm naming less than high school. So that's going to track relative to 11 years where you are. So it's going to end up at 11. If you graduated high school, so 12 years, you get a bump from graduating high school. And then after that, you get not only that bump, but also an additional bump for how much further you got. So here's what we ended up with. And I'll show you how I did all of this in SAS and Stata next week. So first off, does education matter? Big picture question. Do my three slopes work together to capture significant variance in income? What up there tells me yes or no?
P-value.
Which p-value? There's,
Oh,
Less than 0.001.
yeah, this one, model. So, F, why 3? 3 slopes, yes. I have 730 slopes I could have estimated but haven't yet. So ratio of information known to unknown, 47. That's pretty good. P less than 0.05 on that F value. What's MSE again? Leftover variance, yes, residual variance. R square, give me 2 different versions of what this means.
Proportion reduction in variance.
Yep, so by how much did my income variance get reduced? 16.4%. And say it using correlation instead. .404 is the correlation between
Predicted and expected.
the y hat, the predicted from the model using education, and
The observed.
the observed y. Yes, very good. Yeah. So yes, overall, does education matter? Yes, that's my general answer. Of course it does. Why else would you be here, right? Now the good news. I'm assuming everyone here graduated high school? Yes? Probably college too, with some sort of bachelor's degree, science, arts, or otherwise. So if
yep.
expected income at 11 years of education is my beta 0. Now how do I know that? Because that is the point where all of my predictors would be 0. If someone has 11 years of education, that's when this all zeroes out. So it can be tricky to set up your piecewise slopes, but you have to have one point where everything is zeroed out. So at 11 years of education, $8.5 thousand. That's my reference point. The difference in income per year of education between, I guess it should say 2 years and 11 years, is right here. So who would like to put this coefficient in a sentence? It's negative 0.3. I'll start you off. For every
Year of education.
year of education,
Less than 11 years.
yeah, I say, well, under 11, ... income
Is expected.
is expected to go
Down.
down by 0.27. And is that a significant down or a non-significant down? Yeah, non-significant down. So non-significantly lower is probably how I would phrase that. So in other words, if you don't graduate high school, does it matter how far you got? Nope, not according to this. It actually makes it worse somehow. I don't know what that means, but. So now, beta 2. That is the bump for graduating high schools, from going from 11 to 12. So relative to 11 years, those who have 12 years,
High school graduation.
they have higher income by $4.7 thousand, which is
Significant.
significantly higher, yeah. From there, for every year of education after 12, what happens to your income?
It goes up $2,120.
Yes, and for every additional year of education after 12, income goes up by $2,000.
Significant.
Yeah. Can you think of how I would test for a difference across any of these coefficients? Like if I wanted to know if the boost for high school is different than this boost per year, could I do that? Is 4 different than 2? I could do that. That's a linear combination. You know how to do that. It's one beta minus the other. You'll get a chance to practice that as well. So here's my picture. What do you think? How about from 2 to 11? I'm gonna go, that's fine. 11 to 12? Nailed that. How about 12 and on? How does my line fit? Yeah, that is correct. It needs to bend, right? It kind of needs to swoop. So I tried quadratic. Okay, wait for it. No. Log? No. So I have R square. It's not helping. And logit? No. Turns out what I think might be needed is 3 more slopes. Bachelors, like masters, and then PhDs. So for those of you who are going to be bored on Thursday while I'm gone, fit this and tell me if I'm right. The GSS homework data is in example 5. You can play with it if you want. So yes, master's degree apparently is where it's at least in this sample. But too late now, right? All right. So that's all we have time for today. We'll see how I got all of these numbers out of the software package next time. The sorcery that this involved, right? Letter sorcery. Sorcery/job security. So, all right, folks. Let me know if you need help with homework. I will see you next week then. And I'll let you know when your next formative assessment is up.
This is gonna be cheap, but I got a new it's like ruining my guts.
What kind is it?
I don't know. I need to not have it.
I look like it.